And here we are in the textbook. And in the textbook, I'm on page 109. And there's 4 pictures on page 109 about how the derivative of a function may fail to exist. So if we look here at the picture in the northwest corner, and this is, a familiar function to you. This looks like the absolute value function, okay? But the derivative fails to exist at 0. Why? Because as x goes to 0 from the left, the slope is -1. As x goes to 0 from the right, the slope is +1. So the limits from the left and the right do not match. So therefore, the derivative fails to exist when x equals 0. Now, the book refers to this as a corner. That's not an AP term. You don't have to worry about the vocabulary here. You just have to recognize if the limit from the left does not equal the limit from the right, then in chapter 2, we said the limit does not exist. And now we're moving on and saying, additionally, the derivative does not exist. There's another picture where the slopes don't match. Southwest, slopes don't match. Southeast, here you have discontinuity. So this is what? Well, this is the absolute value of x divided by x, where it is defined. All the points are in the domain. So this is there's discontinuity. This is not a continuous function. See, these are continuous. You can trace them without taking your pencil off the paper for all points in the domain. The domain are all reals. Here, the domain's all reals. You cannot do that. So the derivative fails to exist for a different reason. Okay? So we're going to go to example 1. And example 1 says, find all points in the domain. And here's your function. Y equals the absolute value of x take away 2 plus 3, where it's not differentiable, where the derivative fails to exist. Except what? This is why we spent time on this in chapter 1, chapter 2. We're going to compare this is the image. We're going to go back to the pre-image. And the pre-image is here. This picture right here is the pre-image. So for example 1, what happened? The pre-image is the absolute value of x. And the textbook tells us we have a corner here at x equals 0. Here's your image. Well, in order to get to the image, you did the opposite. So this is telling you a shift of 2 to the right up 3. Well, the shift of 2 to the right moves the corner from x equals 0 to x equals 2. So instead of, ready? This is a non-calculator question. So instead of worrying about drawing the picture, all we do is back up, consider the pre-image, and do the transformation to the not differentiable. Now, this tilde means not differentiable at x equals 2. But I don't think we even have to draw that picture for you to see it. It's just the picture in the book slid 2 to the right up 3. And at the same place, 2 to the right up 3, the slope from the left as x approaches 2 would not equal the slope from the right as x approaches 2. Okay? So now, ready? You're going to go to problem number 1. Now for problem number 1, sometimes the problems that they send you to are easier and sometimes they're harder. This one's more involved, but here's it'll help you with what's on chapter 2 on the assessment. So you want to do as best you can. And if you need to peek at the solution as a prompt, you want to do the difference quotient for y squared, which is the graph in quadrant 2, versus y equals x in quadrant 1. So we're going to pause the video, allow you to do that, give you a few minutes to work on this, but the difference quotient is something you're accountable for tomorrow. We're here. Now, I did this problem. You could go back and forth between the picture in the book and this. Picture in the book versus doing this analytically. Here's the picture. Problem number 1. Okay, and you can see they tell you what it is. It's x squared in when x is less than 0, and y equals x when it's greater than or equal to 0. Okay. So now what? So I said, here's my t-chart for quadrant 2. 0. The function squares it, so you'd have 0 squared. Well, my change is going to be to the left. So I'm going to replace 0 with 0 and subtract h. It's not going to matter because you're going to square that. And you're going to do, here's your difference quotient. So on the left, you would get, ready, the function squares this. So you would have 0 squared. Well, we're not, no point in foiling. You'd have negative h the quantity squared, which is h squared. Negative h in parentheses squared is h squared, take away 0 over h. The h's would reduce. The limit as h goes to 0 of just h is 0. So in that picture, that slope of that quadratic is going to 0 in quadrant 2. Over here in quadrant 1, we have y equals x. Here, these h's, see, you have one less h in the numerator because you're not squaring it. So these h's reduce to 1. So the fact that h is going to 0 has no effect on the 1. And then you would have the slope in quadrant 1 is 1, which doesn't equal the slope in quadrant 2. So therefore, this is not differentiable as x goes to 0. Okay? This just gives you some practice of the difference quotient. And what you're going to have to do is you're going to see this in Met. And you're going to say, well, it's not my fault. I didn't see it since the end of September. You have to relate the difference quotient to the table. This is telling you what happened. It's y2 take away y1 over x2 take away x1. All right? Next thing, you need your calculator as we move forward. So find your calculator. And we're going to go here. We're going to show you how to do numerical derivative. We're going to walk through this together. Right? The numerical derivative. So what's this question saying, example 2? Compute the numerical derivative of x cubed, comma 2, which is the command in the old calculator. This is the old operating system. You may not have this. I'm leaving this on the PDFs if you have a hand-me-down calculator, and I will show you on the calculator on the laptop if you have the newer operating system. But this command, which is on your calculator, math8, allows you to get the slope of a function at a specific point. So example 2 says you have x cubed and you want to slope it 2. So I'm going over here. You don't need to do this. You just need to look up here. You don't need to do this yet. I go to y equals and I type x cubed. Okay? And when x is 2, ready? You would get to 0.28, which I already have in here. You don't have to worry about that. And for window, zoom 4, I don't see 2.8. It doesn't go up high enough. So I'm going to go to my window and just do a slide. You're not doing this, you're just watching this. It's going to do a slide to the graph to keep it in perspective. So I'm going to add 4. I don't want to do a scale change or the graph would be distorted. Add 4 to the min and max for the y's, and there it is. There's the functions in blue, and if you put 2 as the input, you would get 8 as the output. An example 2 wants to know, what is the slope at that point? What is the instantaneous change of the blue graph at that point? So you could do this. Second quit math 8. Now, see, this is the newer operating system. If you have, an older calculator, you're going to get what's on the PDF. So I want the derivative with respect to x, and you have a choice here. I put it in y1, so I could just put vars, y vars, function mode, y1, or you can type x cubed, either one. And now you want to know, right, in this question, they want to know what's the derivative at 2. Not 222. At 2. Now, remember when we had this issue with y5, with the difference quotient? We have a residual here. We have an error. But we can kind of tell that the slope is 12. So what does that mean? Well, I could draw the tangent to that. I could go to y equals and say the tangent would be 12. That's the slope. X subtract 2, because that's the point. Slide it up 8, right? Draw a graph. The red line is the tangent line, because that red line has the same slope as the blue graph has at that specific point. Okay? So what this is telling you, here's, ready? We typed it one way on the screen. Here's the older way to do it. Math 8, it's the same command. X caret 3, comma, with respect to what? With respect to x, comma, where? At 2. Okay? So that's your model. You're going to 17, which is pretty straightforward problem. All right, there really wasn't anything to it, just pushing some buttons. So we go over here, ready? We type this in there, 4x plus a negative x squared. At 0, the slope is 4. So the picture would look like this. My y equals would change. at 0. What they're telling you is the slope, as this curve goes through the origin, it has a slope of 4. So the tangent graph, you could draw the tangent if you cared to, would just be 4x, because that's the slope of the curve. You don't have to slide it at all, because it's at 0. There comes the tangent line. It's tangent to the curve at the origin. This red graph, this linear equation, has the same slope as the blue graph when x is 0. When x is not 0, it'll have a different slope. Okay? Now, first thing is we're all going to do this. On your calculator, you're going to put that in Y6. Now, ready? Y5, we have our difference quotient. Y6, you're going to put numerical derivative. But the difference is, instead of it equaling a specific value, we're going to have x equal x. Now, you're both based on Y1, okay? Whatever we typed in Y1. So we could just proceed with problem number, whatever it was. Problem number 17. It doesn't matter what we have in there, right? But you're putting in numerical derivative. Vars, y vars, function mode, y1, comma, x, if you have the old operating system. And I'll show you what it looks like. Ready? If you have the older operating system, it looks like this. N deriv y1, comma, x. It's the same commands. It's just the order you put the commands in. See, because you're putting the function with respect to this variable and when all the time. Whereas here, you're typing with respect to this first, then the function, then when. Okay? So look what happens. If I get down to turn on, ready, Y5 and Y6, table set, start at 0, make the delta table 1, second graph. See what this is telling me? It's giving you the slope. Well, we already did this. The slope at 0 of the curve is 4. Here is our difference quotient. We've got an error in there. It's not a big error. 1,000, it's off by. Well, we stored a value in H. In the calculator, it's actually in the book on page 111, how the calculator gets your Y6, which is a different derivation than the difference quotient. But then look how close these are. So the point is, it's two ways of doing the same thing. The benefit of this is Y5 depends upon this H. And if we mistakenly put the wrong value or we type over the H with something else, we're going to get an output, but we can't count on it. This, we don't have that issue with Y6. Now, just so you know, this was too good to be true. And it is too good to be true because, first off, half the test is without a calculator. But in the book, fooling the difference quotient. So they're giving you an example that if this is not infallible, and they're telling you if you put in the absolute value of x and did the numerical derivative at 0, it would give you an answer, which contradicts the picture on page 109. So you just have to be aware, this thing works most of the time, but you have to balance it with your numeracy skills. You can't just say, oh, well, you know, that was the answer on the calculator. That's exactly what's going to happen on a multiple choice exam. They're going to give you, they're going to do the problem wrong on purpose to see what the possible outputs would be. Okay? Now, last thing for today. In the book, on page 112 at the bottom, you have this. Differentiability implies continuity. It's an if-then statement. If the function is differentiable, then it's continuous. Okay. But the converse error is you cannot exchange what's in front of the if with what's in front of the then. So if something's continuous, that does not imply it's differentiable. This is a one-way street. So if we go back here, 3 of these pictures are continuous. But none of them are differentiable at 0. Okay? These 3 pictures, graphs are continuous. You can trace this with your finger or pencil without picking your pencil up off the paper for all points in the domain. But it's not differentiable. The other way around. If you know it's differentiable, then you can assume that it's continuous and you would be correct. Okay? So